Alright, welcome everyone to the multiplication counting principle and permutations. This is the second and last lesson in this chapter, and we're going to introduce ourselves to this way of counting that is used in probability. And it might have been useful to know this a couple of lessons ago when we used the tree diagram, but we're going to talk about it today, so no worries here. Alright, let's get started. So here are our objectives for today. There are three in general. We're going to talk about the multiplication counting principle, determine the number of ways to complete a process involving several steps. Okay. Use factorials to count the number of permutations of a group of individuals, and finally, compute the number of permutations of n individuals taken k at a time. So, a lot of different things going on here, but I assure you this is not super difficult, and you've probably seen this before in like your Algebra 2 class, or maybe even your pre-calc class. So let's go ahead and get started. Last time, we talked about the multiplication rule of independent events, and basically how we multiply their probabilities together to obtain the probability of their intersection. Okay, so we're going to look at another aspect of probability that involves multiplication today, which is counting. Counting is actually fairly difficult, so if you consider yourself a counting master, you may be surprised at how difficult it could be. Alright, first, let's talk about the counting principle. So, the counting principle tells us that for a process involving multiple steps, so let's say k steps, suppose that there are n1 ways to do the first step, n2 ways to do the second step, and nk ways to do the step k. Okay. The total number of different ways to complete the process is simply multiplying all the step ways together. So, how many ways to do step 1 times how many ways to do step 2, times all the middle stuff, and then finally times the final way to do step k. This is called the multiplication counting principle. So let's get right into the examples. Suppose you're eating at a restaurant and you're offered the following menu, alright, where you have a choice between appetizer, main dish, and dessert. How many different meals could you have at this restaurant? Well, currently, the only way you know how to do this is by doing a tree. Okay, so let's go ahead and take a look at the tree where here's our first step, appetizer, okay. Main dish is our second step, and dessert is our third step. Alright, so if you remember the tree diagrams, this is going to be a vertical one, so it might look a little different from the ones you're used to, but here it is. Okay. You see that first step is the appetizer at the top. You select that one first, and then of course you have a main dish to select after that, and finally we have a dessert. Now if you counted all the end results, the end branches together, that would actually give you a total of 24 outcomes. So there are 24 little branches at the end of the tree. But that seems to be a little time consuming to have to make the tree every time to count the number of outcomes. So let's use the multiplication counting principle. Okay. There are 3 ways to do the first step. There are 4 ways to do the second step, and there are 2 ways to do the third step. Okay, I'll go back to this table real quick. Okay, here it is. So how many ways, or what would it look like if we use the multiplication counting principle? Okay, hopefully you've given that a shot. So if you wrote it correctly there, you should end up with something that looks like this. You've got 3 appetizers, 4 main dishes, and 2 desserts. Multiply all those numbers together for a simple, nice, and easy 24. And we already know from me telling you that there are 24 outcomes at the end of the branches, representing 24 different outcomes. Alright, I'll give you another try. Okay, so here's an example for you to try on your own. This is an Uno problem. So there are 4 colors in Uno. I think we all know that. Hopefully you've played Uno before. Each category contains a card of the 10 digits. Okay, so if you form a 4-card hand using only digit cards, and each card in the hand is given to you from a different color, how many different hands are there in total? I'll let you give a shot at this one, and we'll talk about it in a sec. Okay, and if you're back, then you've probably given it a shot. Remember, there are 10 digit cards per color category, so there's 10 red cards, 10 blue cards, 10 yellow cards, and 10 green cards. So when you have all those written out, each of those fulfills a different category, a different item. you just multiply all these things together for a grand total of 10,000 different hands. Okay, to start with, if each of your cards is a digit card, and also they're from different color categories. Next on our list here we have permutation. So permutation is a distinct arrangement of some group of individuals. That's pretty vague. So let's give ourselves a little bit of an example to kind of see what we're talking about here. Some examples of permutations include drawing from a standard deck to form any kind of hand, right? As well as picking the order for which class you want to complete work for. So assuming you have a 6-period schedule, which I'm not sure if any of you guys have since you're all seniors, you'd have to pick from 6 classes to start with. Okay, and once you finish the work for the first class, you only have 5 left. So then you go down to the 4, the 3, and the 2, and the 1 until you run yourself out of work. You complete all your work. Okay, so essentially, you're arranging some individual group. Now, when I say individual, doesn't necessarily mean people. Could be anything. Could be any item you're trying to count. Okay, cards, classes, that kind of stuff. So, in order to kind of describe the second example, the one where you're completing work for classes, we use this thing called a factorial. So if we say n factorial, that is the number described with the n, okay, multiplied by the number below it, and then multiplied by the number below that, until you reach 1. Okay, so you're going to start with the first number, and you're going to multiply by every number between that number and 1. In this case, we have 6 times 5 times 4 times 3 times 2 times 1, which we could also very well write as 6 factorial. Okay, there's also this thing called a permutation formula. Now, I really think this is not very necessary for permutations, but I'm going to offer it to you anyway, just in case you think about this a little bit more, similarly to I like to keep these formulas in hand. Okay, this is something you can use. Essentially, if you want n individuals to be counted, taking k at a time, where kn, okay, using the multiplication counting principle or with a formula, and permute k, this is the formula for it, where n is your factorial at the top, and then you subtract however many spaces you need on the bottom for a factorial. And of course, definition of 0 factorial is 1. Let's take a look at this in action. So how many different outcomes to form a 5-card hand with a 52-card deck? Okay. Well, this might seem familiar to you if you were paying attention in the last couple of lessons. Okay. So I'll go ahead and kind of set it up for you real quick. Here's the first card you draw. How many outcomes are there in there? Second card, third card, fourth card, and fifth card. Okay. How many different ways can you fill with these? All right, welcome back. Hopefully you gave it a shot. This should look very, very familiar. This is actually just the chance, okay, or rather not the chance, but we're talking about the denominators from those previous problems involving cards. You have 52 cards here, 51 cards here, 50, 49, and 48. Okay. And then you multiply these all together, okay, we end up with our final permutation. Of course, that's a very large number, and I don't have it off the top of my head, but this is essentially what that number would be. All right, if you are looking for the permutation way to do it, here's what that looks like. You have 52 factorial over 52 minus 5, all in parentheses, factorial, which would give us 52 factorial over 47 factorial. And of course, you can simplify that number, but it is still very large and very in charge. Okay, a huge distinction I want to make for permutations is that the order matters. Later we're going to learn about combinations, which order does not matter in those, but it is very similar. So another example I'm going to give you of a permutation is if you have a bunch of chores, for examples, you probably wouldn't want to do the same chore twice, and you probably wouldn't need to. Same thing goes for when you're doing homework for your classes. You don't need to do the homework for your same class twice. So once you have picked a class to do in the order you give it, okay, you're thinking of, then you used up that class, and so the remaining number of classes goes down by 1. Another word for this would be without a replacement. Okay, if that rings a bell for you. But that's essentially what we're talking about with permutations here. And that's the lesson. So after this video, can you use the multiplication counting principle to determine the number of ways to complete a process involving several steps, and then use factorials to calculate the number of permutations of a group of individuals, and compute the number of permutations using the formula? If you think you can do all of that, then you've prepped well, and I will see you in class.